teaching, and this is not an ideal time, so we're going to work on getting us a little bit later for my middle and high school friends. So yeah, just let that know. So I'm recording, and we are going to get started in just a second. All right. So welcome everyone to Engaging Earth Science Students in Student Science Performances. I am Alana Davis. I am the K-12 Science Professional Learning Specialist for the school district. I am the second half of the Science Department. Christian Callie is your K-12 Science Supervisor. And we make up the science department over at the Instructional Support Center. So keeping with our priorities, our science department priorities for the year, today we're going to be focusing on teachers will utilize phenomenon to drive instruction in the classroom, and teachers will move instruction from one dimension to 3 dimensions of science instruction. So we're going to be diving into how to utilize student science performances in the earth science classroom. This is our balanced science instruction document. This is on our academic website. This lays out how we suggest and promote science instruction within the Cobb County School District. As you can see, we have our 3 dimensions represented. The top level is our science and engineering practices, and that's what our students are going to be expected to do in the classroom. And then we have our cross-cutting concepts, which are those ideas that cut across the science disciplines, like patterns and cause and effect. Those are what science and engineers, it's how they think. And then we have our scientific foundational skills, or our disciplinary core ideas. Those are the science concepts that we actually teach. And that is what scientists and engineers know. So we have what they do, what they think, and what they know. All right. So student science performances, what is that? What are they going to be doing? And what does it look like in our classrooms? So you hear the word phenomenon a lot, phenomena a lot in 3-dimensional science instruction. And what we're talking about when we talk about student science performances, they do these performances to make sense of phenomenon, right? Making sense is the process by which students construct meaning and usable knowledge that becomes more comprehensive over time. And when our students engage in making sense of phenomena, they're using questioning, collecting and analyzing data, they're utilizing evidence, and developing models to support explanations and solutions. So if that sounds foreign to you, it might sound foreign to you. I hope not. But this video this is by Paul Anderson, who is an amazing science guru around the United States. He's nationally well known. And he has developed the website called The Wonder of Science. And this is a video kind of explaining 3-dimensional learning and the impact it can have on our students.
A phenomena is simply something occurs in the real world. So this interview is a phenomena. What just happened a second ago was a phenomena. And so in science, we try to look at things that are more interesting than this interview. So we try to find things that are science, and then kids try to explain it. So we put them in the position of the scientist. And so if a phenomena is something that we observe, then there's got to be things that we do. And so one thing we could do, if we go through the 3 dimensions, there's practices, cross-cutting concepts, and then disciplinary core ideas. So the disciplinary core ideas is what we learn, the science and engineering practices is what we do, and then the cross-cutting concepts is how we think. So if I were to think about an apple falling from a tree, there's going to be me asking questions like, why does it fall? There's also me trying to understand the science of gravity and why it's falling. But then I should be thinking about cross-cutting concept of cause and effect, what's causing it to fall. And so if we define it as what kids do, what they learn, and how they think, you need all 3 of those dimensions to understand science, just like we need all 3 of those dimensions to understand just the real world. The old science classroom, we would just go through content. So you'd come into a science classroom and the teacher would say, we're going to learn about gravity, and this is a force of gravity, and objects are a distance apart, and they pull on each other. And so we would do all the explanation at the beginning, and then at the end you do a lab. So what you're really doing is not science. You're just explaining to them, and then they eventually get to explore a little bit. And so what does it look like? What does the classroom look like where it's really 3-dimensional? Is we just do the exploration first before we do the explanation. So in a classroom, kids should be in the role of the scientist. What does the physical classroom look like? Everything I just described, like the cross-cutting concepts and what those are, how we think, the science and engineering practices, those should all be used in the space itself. So that I can explicitly say to kids, like right now you're asking a question, what are the elements of a good question? So like when I go into a classroom, how I can judge if it's a three-dimensional classroom is, number one, the teacher shouldn't just be talking, the kids should be exploring. And what I do when I go into the classroom is I go immediately to a kid and just say, what are you trying to figure out today? And if they can tell me that, then it's probably three-dimensional. If they're like, we're learning about gravity, then they're probably not doing three dimensions. The greatest impact I've seen it is at the elementary, and that's an area where a lot of the time we don't get science going on. But those kids who are kindergartners or grade 1, they lived in the natural world for 5 years, and so they have a fundamental understanding of the natural world. And if you remember what a kindergartner was like all that happens with a kindergartner is just wonder flies out of their head. And they understand science just as well as we do. It's not like somehow we learn more science than they do. And so I think the coolest thing is if you just let the kids talk and let them ask questions and let them investigate, you start to value the kid as an investigator, and more importantly, the kid as a important human.
All right, so that was just giving us a brief overview of three-dimensional learning and what that looks like in the classroom or what it should sound like and all that good stuff. So let's specifically look at student science performances. So when students are engaged in making sense of phenomena, they're using those science and engineering practices, multiple ones, cross-cutting concepts, and those core ideas. It creates an opportunity for them to gather information and data, reason relationships, and communicate explanations supported by evidence. So let's look at it a step further. Let's look at the practices. So when we're speaking in terms of science and engineering practices, that's what students do in science. We do. Much like playing a sport, we engage students in performances to show us that they can do those sciences. So if you'll look on the left-hand side of this chart, you see our science and engineering practices, asking questions, obtaining and evaluating information, planning and carrying out investigations, models, and so on. Those are embedded within our GSE science standards in our elements. That's an added bonus for us as teachers. So it's telling us exactly what our students need to do in their science performances. Here is what those science SCPs are promoting. So when our students are asking questions, it's promoting curiosity. We want to promote creativity. We're promoting language skills, speaking and listening skills throughout all of these science performances because they're going to be actively engaged with the practices. So when we talk about student science performances, it's in a very specific sequence. It's called a GRE sequence. Much like you've probably heard in the past, a 5E lesson plan. A GRC stands for gather, reason, and communicate. So our students are going to be gathering evidence, they're going to be reasoning that evidence, and they're going to be communicating their results or their thinking to us. During the gather portion of a lesson, a student science performance lesson, we're going to give our students data and information, and they're going to analyze that and evaluate it. And they're developing evidence at the same time to help them understand the causes of the phenomena. During the reason portion of the lesson sequence, the teaching moves beyond simple communication of collected data, and your students are going to be working together or independently to construct an explanation for the causes. So they're going to have to really look at the data that they've collected, look at research that they've done on their own, and come up with a reasoning behind why they think something is happening. And during the communicate portion, you're going to have class discussions, and students are going to take turn presenting their reasoning for the causes of the phenomenon and reflecting on their own learning. And this can be used for formative and summative assessments, this piece of the lesson sequence. So here is the GRC sequence again. We first gather information, then we reason with the evidence, and then we communicate our reasoning. Here are how the practices fall within this continuum during the sequence, I'm sorry. So you see during the gathering portion, they're going to be utilizing several science and engineering practices, also within reasoning, and at the end as well. So lots of practice with those. Okay, here is an example of a student science performance for the same core idea, so the same science topic of structure and function across grade level bands. Now, this isn't an earth science specific one, but it is what it is. It's just an example I found out of the resource I'm using. So K2, so just so you can see the progression. K2, students are constructing an explanation for ways some plant structures help protect them from being eaten by animals. So they're going to do research, ask questions, get some data, and then make a claim. Third through fifth, same idea, structure, and function. Students are going to obtain information from readings to investigate how the structures of 3 different types of seeds function to meet the needs of the plant. All right, so we're taking that rigor up a notch, and we're not just constructing an explanation, we're gathering information from actual readings and then doing an investigation. Middle school, students develop an argument for how the evidence they have gathered supports the explanation that a cell functions as a system that contributes to the functioning of the plant. And then taking a step further, bumping it up, high school level, students develop and use a model, it's supposed to be and use a model to illustrate how the hierarchical organization of interacting systems function to support the motion of a chicken foot. So this is all centered around structure and function. That's just an example. So let's look at an example of an earth science student's performance for middle school. Okay. Now, I'm utilizing Brett Molding, who is like the grandfather of the new framework for science instruction and three-dimensional science and the NGSS standards. I'm utilizing 2 of his books that he has written, and his books are written to NGSS. So I pulled this and correlated it to ours. So the phenomenon that you share with your students, you can share with a video, just talking it out, or however you want to share the phenomenon with your students. You're going to do that first. The phenomenon is the position of Venus and the moon relative to one another and their positions above the horizon change each night. That's it. That's the phenomenon. Here is what your student is expected to do. This is the expectation. They have to construct an explanation for causes of the changes to objects in the solar system that results in both the motion and the apparent motion of the moon, Venus, and Earth. All right, notice how everything is kind of color coded. The blue is our science and engineering practice. So they're going to be what they're going to do. They're going to construct an explanation. The green is the cross-cutting concept. So we know that cause and effect and change is a cross-cutting concept. And then the orange or gray, like what, or that's not gray, it's like brown, burnt orange, is your disciplinary core idea. All right. So that's what we're expecting them to do by the end. Here is where the performance is broken down into the gather, reasoning, and communicating sequence. So first thing, students are going to obtain information from reliable sources to develop a model that describes changes in the motion of Earth, Moon, and Venus. That's the first thing that they're going to do. A student science performance is always step-by-step instruction. You're going to need to give them those reliable sources. Step 2. Next performance, students construct an explanation for why changes in the position of the moon and Venus are caused by the moon orbiting Earth, Earth spinning on its axis, and Venus moving as it orbits around the sun. They can do this independently in a small group, just with one partner, however you want it. But you're stopping after each of these. This might take several days, several sections of class to complete a student science performance. But you need to have discussions after each step of the process as well. That's valuable teaching moments. Okay, so after the first 2 performances that students are doing, then you're going to have a class discussion. Here are some possible questions that you could ask them to further along their understanding and connection to the cross-cutting concepts and that core idea. to help them really understand the fundamental cause for this phenomena to happen. So after you have that class discussion, you are going to move into, I just want to make sure. Yeah, the last part. So you're communicating part of the lesson, which is students construct an explanation for causes of the changes in the relative position of objects in the solar system based on the motion and apparent motion of Moon, Venus, and Earth. So constructing explanation, we realize that students are going to have to communicate something. Does it always have to be written? Absolutely not. Can they make a video explanation? Yes. We can offer them choice and voice in how they present the information to us, the explanation, as long as they have the causes for the change. All right, so looking at this, each of the 3 student performances above use core ideas to explain the phenomenon, cross-cutting concepts to focus students on specific aspects, and utilizes practices to gather evidence to make sense of the phenomenon. And this is an example right out of Molding's book, Science is Phenomenal. Now, more examples, or here's how we can support, sorry, before I jump to sharing all of my secrets. How can we support student science performances? So in this table, you can see the information. So you have your sequence of the lesson, gather, reason, communicate, and apply beyond. What the student is going to do, so the student performance. And then on the right-hand side is how we can provide guidance and support for them during those sections. Nowhere on here does it say give students the answer or show them exactly why something happens. In 3-dimensional science instruction, we don't give them the answers right away. They have to work for it. They actually have to do some research and some investigation, come up with their own questions and answer those questions. So this is just some helpful hints on how to support your students through the different parts of the GRC sequence. For example, while they're gathering information and asking questions, support students by helping them develop relevant questions and facilitate them making connections. During reasoning, help students to develop skills to actually analyze data. That's a skill that we know has to be taught to them, to look at something critically, especially mathematical data that we're looking at. And then during communication, establish multiple opportunities for students to produce and revise their models. They might have to. That's all part of scientific thinking, is revising our claims and editing our evidence and coming back and figuring out exactly and reasoning what is happening and causing something to happen. All right, where can you find more gather, reasoning, communicate, student science performance examples? I hit the jackpot. So Brett Molding has a website that is free. If you go to his website, it's called Phenomenal GRC Lessons. They have middle school lessons. And if you click on the middle school, you can see they have life science, physical science, earth, and space science. Here is what that looks like. It's a complete template, or you have now this is NGSS, so you're going to have to pick and choose. There's a link to the lesson topic with photo, a phenomenon, if it's GRC or 5E, and notes for you. And they're all student science performances. So I'll click on one just so you can see what it looks like. Uh-oh. It can be done at home export. It's not letting me. There we go. Open preview. So it is written the exact same way. This is the GRC template. It's very, very extensive. But you have it just like I showed you, student science performance, what they need to do every time. You have your teaching suggestion portion of it, how to formatively assess. I mean, it's all of your appendixes that you can give your students. It's good stuff. Here is high school, not as many, but still there's some opportunity for you to utilize some of these student science performance lessons. These are the two resources that I use today on student science investigations. You have Teaching Science is Phenomenal by Roger Bybee and Brett Molding, the godfathers of NGSS. And then his newest book, Engaging Students in Science Investigation Using GRC, is this book right here. So if you would like to borrow those, let me know. And that is what I have for you today. And let's see, can you please send the website to us? Absolutely. I'll put it in the chat right now. Oh, did someone already do it? Here is, it's called Going 3D with GRC. Putting it in there right there. There it is. Yeah. Any questions from my friends that have joined today? Oh, thank you. It's blocked for you. I don't know why, Angie. Same for you? It's blocked?
It's a Google Doc. It's a Google Doc. So like I probably could do it at home, but Google, you know what I mean? So
Yeah.
sorry, but yeah, it's blocked.
Yeah, and I don't have a county laptop, so that's why.
Okay.
Yeah. So just do it from your home computer. Because
Y'all,
huh?
I don't have one.
Oh, what about a desktop? I guess it would be the same thing.
Is there
A
any
lot
way
of-
that we can?
Okay.
We could do a help ticket
Yeah.
and get them to
Oh,
unlock it.
okay, do that. Or if you can somehow, I could send you, trying to think if I could send anything. No, I was saying you can tell me which ones you want and I could like download it and give it to you. Because I
That's a lot
would.
on you though.
I know, but yeah, does it make a difference whether you're in Chrome or Edge? I don't know if that has anything to do with it. Brittany says use Barbara's. Okay, so Barbara has a different one and it works. So up here, guys, this Google Doc one that Barbara put, try that one. Okay, cool. All right, I'm gonna stop recording.